This is Bob Capetta, and this lesson is on linear programming with graphing. So we're going to look at the following question for this lesson. We're going to have to find the maximum and minimum value of a function. So I'm going to say find the max and min values of z, which equals 2x plus 5y, subject to the following constraint equations. 3x plus 2y less equals 6. Negative 2x plus 4y is less equal to 8. X plus y greater or equal to 1. X greater than or equal to 0. Y greater than or equal to 0. So we have 5 constraint equations. These last 2, though, tell us that it's going to be in quadrant 1. So we don't really need to worry too much outside quadrant 1. We want to go ahead and construct our feasible region together with the corner points, and then we'll test those corner points to determine what's the maximum value and what is the minimum value. So for clarification, this inequality is going to define line 1. This inequality is going to define line 2. And this inequality is going to define line 3. We want to go ahead and graph all 3 of those, find the feasible region, and then work accordingly. All right. So the first one we have is 3x plus 2y is less than or equal to 6. We're going to go ahead and use intercepts to graph that. So let's take a look at our first line. Again, 3x plus 2y less equals 6. To graph an inequality, we're first going to graph the equation. 3x plus 2y equals 6. Setting up the intercepts. If I let x be 0, what is y? If I let y be 0, what is x? If x is 0, 3 times 0 plus 2y is 6. 2y is 6, y is 3. So if x is 0, y is 3. That is the y-intercept. If y is 0, 3x plus 2 times 0 is 6. 3x plus 0 is 6. 3x is 6. X is 2. So those are my intercepts. I have 0, 3, and I have 2, 0. Let's go ahead and graph that line. 0, 1, 2, 3 here. 0, 1, 2 here. So here is 0, 3, and here is 2, 0. Let's go ahead and graph that line. I'm really only concerned about what's happening in the first quadrant, but I'll extend it beyond just a little bit. Now remember, this is an inequality. We have 3x plus 2y is less than or equal to 6. The point we always like to check is 0, 0. So do I shade towards 0, 0, or do I shade away from 0, 0? So this will be our standard approach. Testing 0, 0, so we have 3 times 0 plus 2 times 0 less equals 6. 0 plus 0 less equals 6. Yes, that's true. So we're going to shade towards 0, 0 under that line. That's what we need, and this is my first line. This is line number 1. Now remember, we had 3 lines to work with. We want to construct our feasible region based on those 3 lines. Let's go ahead and do our second one. So we have line 1 here. This is line 1. This is line 1, so we can refer to that later. And then we're going to go ahead and do our second line. So our second one is negative 2x plus 4y less equal to 8. Let's write that down. negative 2x plus 4y less equal to 8. We're going to go ahead and do it as an equation. Negative 2x plus 4y equals 8. Same approach. X, y, x is 0, what is y? Y is 0, what is x? If I plug a 0 in for x, negative 2 times 0 plus 4y is 8. 0 plus 4y is 8. 4y is 8. Y is 2. Plug in a 0 for y. That'll give me negative 2x plus 4 times 0 is 8. Negative 2x plus 0 is 8. Negative 2x is 8. X is negative 4, which is certainly outside the first quadrant. Okay, so what am I going to do? X back 4, 1, 2, 3, 4. Y up 2, 1, 2. These are our 2 points that make line 2. This is line 2. This is line 2. So we're going to go ahead and we're going to graph that line, and then we're going to test to see if we go towards 0, 0 or away from 0, 0. Again, outside the first quadrant, I don't care that much. But 0, 0 is here. Do I go towards 0, 0 or do I go away from 0, 0? Our inequality is negative 2x plus 4y less equal to 8. Test 0, 0. Again, our favorite point to test. So negative 2 times 0 plus 4 times 0, is that less equal to 8? Is 0 plus 0 less equal to 8? 0 less equal to 8. Yes, so I shade towards 0, 0, so towards this way. So we'll be under this line, and that's line 2. So you'll notice we had line 1, we were under that line. We had line 2, we were under that line. So towards 0, 0 in each of those first 2 cases. Now we're going to move to line 3, which is x plus y is greater than or equal to 1. So let's do that quickly. That one's easier than the first 2. X plus y greater than or equal to 1. This is our third line. So the line part is x plus y equals 1. And I hope I can jump to the chase and recognize if x is 0, y has to be 1. If y is 0, x has to be 1 for line 3. So in terms of our graph, there's 1, there's 1. There are our 2 intercepts, our x and y intercepts. As we graph those, again, first quadrant is really all I care about because x was greater than 0, y was greater than 0. Do I go towards 0, 0 or do I go away from 0, 0? So testing 0, 0, what do we have? X plus y greater than or equal to 1, 0 plus 0 greater or equal 1, 0 greater than or equal to 1, that's no. So we do not go towards, we go away from 0, 0. So we have 3 lines. We want to go ahead and construct one feasible region that will define those 3 lines. So we've got to put all those together. Let's do that. Line 1, line 2, and line 3 on the same graph. So let's collect all of our information that we need. So what did that look like? Line 1 had the following intercepts. Line 1 was 0, 3, 2, 0. 0, 3, 2, 0. We went towards 0, 0. That was line 1. Line 2 was 0, 2, negative 4, 0. 0, 2, negative 4, 0. and also towards 0, 0. And then line 3 had what? Line 3 was 0, 1, 1, 0. And it was away from 0, 0. So let's go ahead and do our best to draw that feasible region and identify the corner points. So we've got to go up to 3 in the y range. 0, 1, 2, 3. X only goes out to 2. Here, 1, 2, but back to -4 here. 1, 2, 3, 4. So we'll start with line 1. Line 1 was 0, 3, 2, 0. Let's go ahead and draw that in, and we're shading towards 0, 0. So I'm only going to shade that portion that is in the first quadrant. So it's towards 0, 0. So I'm going to put a little green lines here telling me to go that way. And this is line 1. Line 2 was 0, 2. And -4, 0. So if we draw that in, looks like I'm going to draw that one by hand. But again, I'm really only concerned with this portion that's in the first quadrant, and that's also towards 0, 0, so it's going below. So in the first quadrant, below this line in purple, below this line in black, puts me in this corner. And then finally, I have 0, 1, 1, 0, which is here. So my region of interest looks like this, below this line, below that line, above, away from 0, 0 here. So this is my feasible region right here. So I have my feasible region. I need to find each corner point. So how do I do that? Well, line 1 was here, line 2 was here, line 3 was here. So this is a corner point. This was 1, 0. This is a corner point. That's 2, 0. This is a corner point. That's 0, 1. This is a corner point. That's 0, 2. This is not a corner point. 0, 3 is not a corner point because it does not bound the feasible region. Remember, the feasible region is under this line 2. 0, 3 is not under this line 2. But I also need to find the fifth point. So we've got 1, 2, 3, 4 points. The fifth point is right here. That is the intersection point between which two lines. Line 1 is here and line 2 is here. So I need to find intersection. Need to find the intersection point of line 1 and line 2. So line 1 was 3x plus 2y equals 6. Line 2 was negative 2x plus 4y equals 8. I'm going to choose to multiply this first equation by negative 2. Negative 2 times 3x is negative 6x. Negative 2 times 2y is negative 4y. Negative 2 times 6 is negative 12. We're going to add that to our second equation, which is negative 2x. plus 4y equals 8. You'll notice the y's go away, and I get negative 8x equals negative 4 divided by negative 8. And I get x is 1/2. So the x value is 1/2. I need to figure out what the y value is that corresponds to an x value of 1/2. So I can plug it into one of these equations. Maybe I'll plug it into negative 2x plus 4y equals 8. So I've got some room up here on the top of my page. So the other equation is negative 2x plus 4y equals 8. We said x was 1/2. Negative 2 times 1/2 plus 4y is 8. Negative 2 times 1/2 is negative 1. Plus 4y is 8. Adding 1 to both sides, 4y is 9. Y is 9/4, or 2 1/4, a little bit more than 2. Yeah, that looks like that's about right. So this other intersection point, this other corner point, x is 1/2, y is 9/4. So you'll notice we've identified 5 corner points. 1, 2, 3, 4, 5. Again, I want to emphasize this one, 0, 3, is not a corner point. It does not bound the feasible region here because it's not underneath line 2. So now let's go back and look at our original question. What did we have? We were supposed to find the maximum and minimum values of 2x plus 5y subject to all of those conditions. Well, we have all of our corner points. So what we're going to do is we're going to list the 5 corner points. Plug the corner points into that function, see what we have, and then from there we can identify the minimum and maximum value. So corner point, we had 0, 1 was a corner point. We had 0, 2 was a corner point. We had 1/2, 9/4 was a corner point. We had 2, 0, and we had 1, 0. Where those corner points come from? Again, let's take a look at our previous page here. 0, 1, 0, 2, 1/2, 9/4 here, 2, 0, and 1, 0. And our feasible region is all this stuff here. So we're going to plug those corner points into 2x plus 5y. So this is my corner point x comma y, and then I need z equals 2x plus 5y. I'm going to use my calculator to help with this. If you can see that, that's great. I'm going to say 0 store in x, comma 1 store in y. And then we're going to look at 2x plus 5y. Nope, doesn't like that. 0 store in x, 1 store in y, 2x plus 5y is, of course, 5. 2 times 0 plus 5 times 2 is 10. 2 times 1/2 plus 5 times 9/4 is 12 1/4. 2 times 2 is 4, plus 5 times 0 would be 4. 2 times 1 is 2, plus 5 times 0 is 2. So it appears as if z obtains a maximum value of 12.25. When x equals 1/2, y equals 9/4. You can find the minimum value. Z obtains a min value of what? Z obtains a min value of 2 when x equals 1 and y equals 0. What was nice about this was we had a bounded region. If you have a closed bounded region, you will have a minimum and a maximum value on there. So looking at our picture, again, in a situation like this, 1, 2, 3, 4, 5 sides, closed and bounded. Your feasible region is a closed region like that. You will always have both a minimum and a maximum. And that will conclude this lesson.